Water is life, and drinking water absolutely vital. The climatically induced shortage of drinking water threatens life itself in many parts of the world, a problem magnified by the discharge of all kinds of wastewater, which dramatically reduces the amount of drinking water available worldwide. For that reason, minimizing water contamination has to be one of our top priorities. Industrial wastewater, and in particular leachate from landfills, should no longer be allowed to enter the water cycle in an unpurified state. So the challenge facing us today is to gain additional supplies of drinking water and purify wastewater. Salt water and contaminated water have one thing in common. Both are solutions made up of molecules, salts and other solutes of differing origins. Consequently, desalination technology can be used to purify the leachate from landfills as long as the problems specific to wastewater are overcome. The problem sounds quite simple. How can the pure water be separated from seawater or leachate? There is a law of nature which at first glance would seem to achieve exactly the opposite result of what we want. This law, known as osmosis, is a natural process which controls the water household in the cells of every living creature. Let's have a look at this model of what goes on. Theoretically, we can say that two solutions of differing concentrations, separated by a membrane, will try to equalize the difference in their concentrations. Both the smaller water molecules and the large solute molecules would diffuse unhindered through the membrane. But a cell membrane is in fact semi-permeable, and so only molecules of up to a certain size can diffuse through. In the attempt to balance out the difference in concentration, the more concentrated solution will suck in the smaller water molecules from the less concentrated solution, with the larger solute molecules being held back by the membrane. The more concentrated a solution is, the greater the osmotic pressure. If we subject the concentrated solution to very high pressure, the small water molecules flow through the membrane and out of the concentrated solution. In this way, the natural process of osmosis is reversed, and thus can be used to desalinate or purify water. The term given to this is reverse osmosis. When reverse osmosis is used for industrial applications, salty or dirty water is pumped into a separating device known as a module. A high-pressure pump ensures the required operating pressure of 60 bar is maintained. The semi-permeable membranes only let the pure water molecules pass through, and they are then channeled off in the permeate stream. The liquid left behind becomes more concentrated as the proportion of solutes increases, and is then pumped away in the concentrate stream. The osmotic pressure of the untreated water determines the yield of pure water, the so-called recovery rate. For example, you only obtain approximately 30% permeate from seawater, which has an osmotic pressure of around 25 bar, but the permeate yield from landfill leachate, with an osmotic pressure of between 5 and 15 bar, is about 70 to 80%. The reverse osmosis system developed by Rochem is based on precisely this principle. Rochem plants have been successfully supplying drinking water by desalination since the early 1980s. By the end of 1992, more than 700 plants were in operation all over the world. Its customers include merchant shipping lines, navies, and companies in the offshore industry. Now, however, this reverse osmosis technology is being increasingly used to purify landfill leachate. Rainwater, spring water and groundwater flowing in from the surrounding soil penetrate the body of waste in the landfill and become contaminated. The leachate produced in this way is usually polluted with neutral salts, ammonium, absorbable organically bonded halogens, oxygen-depleting substances, and other harmful substances such as heavy metals, lead, mercury, and the like. By using reverse osmosis technology, we can even purify this kind of highly polluted wastewater and return it pollutant-free to the water cycle. Rochem's disc tube membrane module has been used to this end with great success since 1988. The concept behind this modular system is partly based on work carried out at the GKSS Research Center at Geesthacht near Hamburg. The system itself is the result of the many years of research and development carried out at Rochem. At the heart of this leachate purification plant is a patented disc tube, or DT module. It is made up of hydraulic discs and octagonal-shaped cushion membranes. Once the module has been assembled, O-rings on the hydraulic discs ensure a leak-proof seal between the high and low-pressure sides of the system. Rochem has largely automated production of these cushion membranes. The membrane material is manufactured in rolls, from which the flat membrane pieces are cut out. Two of these pieces with a drainage fleece in the middle form the basis of each cushion membrane. They are bonded together by machine, and a hole is then punched in the middle. The three components of a flat membrane are a mere 0.1 of a millimeter thick. The actual separating medium, though, is only 2,500 angstrom, or 4,000ths of a millimeter thick, so it is mounted on a carrier medium and a porous supporting fleece to give it the necessary stability. Ultrasonic robots then bond together the membrane and the drainage fleece, and any protruding edges are trimmed off. Constant controls and careful monitoring of the production process ensure high product quality. Once the O-rings have been mounted by hand, 170 hydraulic discs and 169 cushion membranes are fitted, one after the other, onto a tie rod to form a standardized stack of membranes about a meter high. The total surface area of the 169 cushion membranes is 7.6 square meters. After the end plate has been attached and the nuts tightened, the module is completed by inserting it into a tube which serves as a pressurized cylinder for the stack of membranes. Pumped into the module at great pressure, the untreated feed water is forced between the pressurized tube and the stack of membranes to the end disc. From there it flows through the various open channels composed of hydraulic discs and cushion membranes. The arrangement of the hydraulic discs ensures a controlled flow of untreated feed water. It is pumped through the open channels across the surfaces of the membranes. This cross-flow method ensures that the solutes are not deposited on the membrane surfaces even though their concentration increases along the flow path. What's more, the open channel allows for highly efficient cleaning. The permeate obtained by this process is of drinking water quality when the process is applied to desalinate seawater. If reverse osmosis technology is used to purify landfill leachate, the permeate can immediately be returned to the water cycle. But the leachate purification process concentrates these pollutants and substances that are harmful to pure water and the environment. Thermal processes, such as evaporation and subsequent drying, are normally used to concentrate these substances before disposal. But here too, Rochem has developed alternative solutions that greatly reduce energy requirements. In order to increase the yield of dischargeable permeate even further, Rochem has introduced an extra step into the reverse osmosis process, high-pressure reverse osmosis. At a greatly increased pressure of between 120 and 150 bar, the concentrate stream is again forced across semi-permeable membranes in a special DT module, with the result that more pure water is extracted from the concentrate. Consequently, there is a considerable reduction in the amount of concentrate remaining. Thus, the permeate recovery rate can be increased to over 90%. Rochem has introduced standardized testing conditions to ensure that every module is subjected to a comprehensive functional inspection. Only after passing this test does it receive its inspection number and can leave the factory. The successful large-scale application of Rochem's reverse osmosis leachate purification technology began in mid-1988 at a waste disposal plant in Schwabach, a town in southern Germany. Rochem also supplied what is still the world's largest leachate purifying system to Ihlenberg landfill near Selmsdorf in northeast Germany. It went into operation on December the 15th, 1989. In addition to many other sites in Germany, leachate purification plants of various sizes have also been delivered to Austria, the United Kingdom, Ireland, France, Italy, Switzerland, and the USA. Rochem has faced up to the challenges presented by increasingly grave environmental problems. One result has been innovative advances in the technology for purifying contaminated water. Over 50% of the reverse osmosis plants operating around the world for leachate purification were built by Rochem. This company, with its DT module and leachate purification technology, is a world leader in this sector. So, as you can see, Rochem is making an active contribution to the solution of pressing environmental problems to protect future generations.